You've typed a few words, hit generate, and watched as stunning images appear, seemingly out of thin air. It feels like pure magic, but without understanding the underlying mechanics, you're missing out on unlocking the true creative power of AI image generators. Today, we're pulling back the curtain to reveal the intricate process that transforms a simple text prompt into a breathtaking digital masterpiece, giving you the knowledge to truly master this revolutionary technology. Imagine having the power to conjure any visual thought from your mind, simply by describing it. That's the promise of AI image generation, and it's here now. But how do these digital artists actually work? Are they just blindly mashing pixels together, or is there a deeper, more sophisticated process at play? The truth is, it's far more fascinating than you might think, involving layers of complex algorithms that mimic aspects of how humans learn and perceive. Forget about a simple copy and paste function. These systems are actually creating something entirely new, pixel by pixel, based on the concepts you provide. Most people only scratch the surface, treating it as a black box. But once you understand the core principles, your ability to guide and perfect these AI creations will skyrocket. The journey from a simple text prompt to a stunning image is a multi-stage process, primarily driven by what are known as diffusion models. At their heart, diffusion models are trained to do one very specific, very powerful thing: reverse noise. Think of it like this. If you take a clear image and slowly add random static or noise until it's completely obscured, a diffusion model learns to reverse that process. It learns to recognize patterns within the chaos and remove the noise, step by painstaking step, until the original image, or something very much like it, re-emerges. It's an elegant dance between destruction and reconstruction, where the AI becomes an expert at finding hidden order. Now, let's break down the key components that make this magic happen, starting with the initial transformation of your input. First, there's the encoder. When you input a prompt like a majestic lion in a sunset savanna, the AI doesn't just treat that as raw text. Instead, a specialized component called a text encoder translates your words into a numerical representation. Think of it as converting language into a universal mathematical code that the AI can understand. These numerical vectors, often called embeddings, capture the semantic meaning and relationships between words, allowing the AI to grasp the concept of a majestic lion rather than just the individual words. But it's not just the text. The image itself also needs to be understood in a similar way. Instead of working directly with millions of pixels, which would be incredibly computationally intensive, image generators first take your concept and represent it in a latent space. This is a lower-dimensional, compressed version of the image, much like a highly efficient summary. It retains all the critical visual information, but discards the redundant details. Think of it as a blueprint or a DNA strand of the image, containing the essence of its form, color, and composition. Working in this latent space is significantly faster and more efficient, allowing the AI to experiment and iterate much more quickly. With our concept now represented in this compact latent form, the actual creative process begins. The core idea is to start with pure random noise in this latent space. Imagine a television screen displaying nothing but static. This static is our starting point, a completely random collection of pixels. From this chaos, the AI must somehow conjure a coherent image. This is where the denoising process comes into play, guided by your text prompt. The AI's job is to iteratively remove this noise, slowly shaping the randomness into something recognizable. It's like sculpting a figure from a block of marble, but instead of chipping away, the AI is subtracting layers of static. Each step in this process involves the AI predicting what cleaner image might emerge if a small amount of noise were removed. It does this by analyzing the current noisy image and comparing it to what it has learned from millions of other images during its training. The key player in this denoising is often a neural network called a U-net. This U-net acts as the brain of the operation, learning to recognize patterns and subtle structures even within extremely noisy images. It takes the noisy latent image and your text embeddings as input, then predicts the noise component that needs to be removed. It's a bit like a highly sophisticated filter, meticulously cleaning up the signal. The U-net doesn't just remove noise randomly. It's constantly being conditioned by your text prompt. This means your text embeddings are fed into various layers of the U-net, guiding its denoising decisions. If your prompt is a futuristic cityscape at night, The U-Net will prioritize patterns and structures associated with cities, futuristic elements, and nighttime scenes as it removes noise. This conditioning ensures that the emerging image aligns with your textual description, transforming abstract noise into a specific vision. The entire process isn't a single magical leap. Instead, it involves hundreds, sometimes even thousands, of tiny iterative steps. In each step, the U-Net makes a small adjustment, removing a tiny bit of predicted noise, bringing the image closer to coherence. It's a gradual refinement, building complexity and detail with every iteration. This is why you often see AI image generators producing an initial blurry image that slowly sharpens and gains detail over time. Once the denoising process is complete and the latent representation is sufficiently clean, another component, the decoder, takes over. The decoder's job is to translate that compressed, denoised latent representation back into a full-resolution, pixel-rich image that we can actually see. It essentially reverses the process of the initial encoder, expanding the blueprint back into a detailed, vibrant picture. The quality of the final image depends heavily on the vast amount of data the AI was trained on. These models learn by analyzing billions of images and their corresponding text descriptions, scraped from the internet. They learn to associate words like cat with countless variations of feline forms, sky with different colors and cloud patterns, and ocean with waves, reflections, and depths. This massive dataset is what gives the AI its understanding of the visual world and allows it to generate such diverse and realistic imagery. Think of it as an artist who has studied every painting, every photograph, and every drawing ever created. The AI draws upon a similar depth of knowledge, albeit in a statistical, mathematical way. This extensive training is also why prompt engineering has become an art form in itself. Your words are the only way to communicate your vision to the AI. A vague prompt like dog will yield a generic dog. But a golden retriever puppy playing in a sun-drenched field, shallow depth of field, volumetric lighting, hyper-realistic, 85mm lens, gives the AI far more specific instructions, leading to a much more refined and targeted output. It's about learning to speak the AI's language, providing enough detail and context for it to understand your exact creative intent. There are several common mistakes users make that hinder their results. One is being too vague, as we just discussed. Another is expecting the AI to read your mind about stylistic choices. If you want a specific art style like oil painting or cyberpunk, you must include it in the prompt. Forgetting to use negative prompts is also a common pitfall. Negative prompts tell the AI what not to include, like ugly, blurry, deformed, extra limbs, which are crucial for refining quality. Finally, ignoring model-specific parameters like guidance scale or steps can severely limit your output. Experimenting with these settings fine-tunes the AI's creative process. Now, what about pushing the boundaries even further? Tools like ControlNet and LoRa's represent the next level of control and customization. ControlNet allows you to impose specific spatial or structural guidance onto your generated images. For instance, you could provide a simple line drawing or a depth map, and ControlNet will ensure the generated image adheres to that exact composition, even as it fills in the details. It's like giving the AI a precise sketch to color within. Low-res, or low-rank adaptation, are smaller, fine-tuned models that can be added on top of a base model. They specialize in generating very specific subjects, styles, or characters, often trained on a much smaller, highly curated dataset. Want to generate images in the style of a particular artist, or create consistent characters across multiple images? LoRa is your go-to tool. These advanced techniques transform AI image generation from a simple text-to-image tool into a powerful, customizable creative partner. Understanding these underlying mechanisms not only demystifies the process, but also empowers you as a creator. You move from a passive observer to an active director, guiding the AI with precision. The implications of this technology are vast, from revolutionizing graphic design and advertising to enabling entirely new forms of artistic expression and storytelling. It changes how we think about creativity itself. So the next time you generate an image, remember the intricate dance of data, noise, and neural networks happening behind the scenes. It's not just magic, it's a testament to incredible engineering and a glimpse into the future of creativity. Now that you understand the fundamental process, you're ready to explore and master this powerful technology. If you found this breakdown insightful, make sure to subscribe for more deep dives into the world of AI. Stay curious. This is AI Unpacked.